Good morning, students. In our last class, we discussed the molecular orbital energy level diagram for homoatomic, homonuclear diatomic molecule nitrogen. Right? Now, today we will discuss the molecular orbital energy level diagram for oxygen, fluorine, and neon molecules. Students, there is a slight difference in the arrangement of the orbitals in these molecules. Okay, so let's take an example for oxygen at first. Now O2, you know that the atomic number of oxygen is how much, student? It is 8. So here we are going to take it is 1s2, 2s2, 2p, how much, student? It is 4, right? So we will here draw the molecular orbital diagram for the valence shell, and in place of 1s2 we will put it there k shell. So let's see here. So student, here this is the increasing energy, right? And at the ground, if we write down kk star, it means that we have written the first shell bonding as well as anti-bonding molecular orbital. Now we will write it for 2s, right? So we are taking it is 2s2. Similarly, the another oxygen atom, it has will be also having the 2 electrons in its 2s atomic orbital. So this is atomic orbital of first oxygen atom, and this is of the second. Now students, the overlapping will take place, right? And we will get two set of new molecular orbital formed. One is known as a sigma 2s, that is molecular orbital, bonding molecular orbital, and student, this is the excited one, or having the higher energy. This is the anti-bonding molecular orbital. So total how many electrons? 4. So it is 1, 2, 3 and 4. Now students, will come at 2p. This is 2p of one oxygen atom, and this is for the another oxygen atom. So we will write down here 1, 2, 3, and this is 4. Similarly 1, 2, 3 and 4, right? Now students, we will draw the total how many orbitals are there. 3 plus 3, 6. So the molecular orbitals which will be formed will be how much? 6 molecular orbitals will be formed. Among it, 3 will be bonding molecular orbital and 3 will be anti-bonding molecular orbital. So students, this is there. So students, in case of nitrogen, we had here pi 2px and pi 2py, right? But now in case of the oxygen, we will have here sigma 2pz, right? And the pi 2px and pi 2py are raised here. These are pi 2px and pi 2py. Rest will remain the same. This is the only difference. This is their pi star 2px, pi star 2py, and at the top students will have sigma star 2pz. Right now we are going to distribute these 6 electrons. So I not 6, these are 4 plus 4, it's 8 electrons in these molecular orbitals. So here it is 1, 2, 3, 4, 5 and 6. Pi 2px and pi 2py are having the same energy. They are known as the degenerate molecular orbitals. The molecular orbitals which have the same energy are known as degenerate. Right, so 1, 2, 3, 4, 5, 6, and this is 7 and 8. Right, so we have filled up the molecular orbitals here. Now students, we will just write down the electronic configuration here. So the electronic configuration for oxygen molecule will be K star. This is for the first shell. Then we will write down here sigma 2s2, sigma star 2s2. Then students, we have sigma 2pz2. Then comes pi 2px equal to pi 2py, having 2 each, and pi star 2px equal to pi star 2py, 1 on each. Right, now students, from here you can easily find out the bond order of oxygen molecule. Now, as I told you earlier also, to calculate out the bond order, the formula is half Nb minus Ne. So students, here how many electrons are there in the bonding molecular orbital? It is 2, 3, 4, 5, 6, 7, 8. You can either get it through the electronic configuration or from the diagram. So it is 2, 3, 4, 5, 6, 7, 8. And how many electrons are there in anti-bonding? That is Na. It is 2, 3 and 4. So you will write down here 4. So it is coming how much? So the bond order between the two oxygen atom, students, is a double bond will be present between the two oxygen atom. Right? So in this way we have calculated out the bond order of oxygen molecule. Now students, since Nb is greater than Na, therefore molecule is stable, right? And what about the magnetic behavior? Since you can see that in the molecular orbital diagram also, that here we are having the unpaired electron. Since the pi star 2px and pi star 2py is having one electron, unpaired electron, two unpaired electron, therefore it is a paramagnetic in nature. Right, so the magnetic behavior, it is paramagnetic in nature. Yes students, now this was for the oxygen molecule. Similarly students, you can find out for the species also. Let it be O2 negative, right? So here we will directly write down the configuration. So it is sigma 2s2, sigma star 2s2, right? Then we will get here sigma 2pz. In case of oxygen, halogen and the neon, we write down the sigma 2pz at first. Pi 2px equals to pi 2py, then pi star 2px equals to pi star 2py. Students, here earlier we had one electron in each, so now one more electron has been added, it's -1. So you will write down here 2 and it is 1. Earlier it was 1 and 1 in case of oxygen molecule, but now it is a species which has accepted 1 electron. So it is pi star 2px 2 equals to pi star 2py 1. Right, students? Now we can write down, calculate out the bond order. So how many Nb is there? Number of electrons in bonding molecular orbitals, it is 8. And in case of anti-bonding, student, 1 is been added. So earlier it was 4, now it will be 5. So it is 2, 3, 4, 5. So you can easily calculate out the bond order here. It is half Nb minus Na. So students, this will come half 8 minus 5. So it's half into 3, that is 1.5. This is the bond order of O2 negative molecule. And since Nb is greater than Na, therefore O2 negative stable. About the magnetic behavior, presence of unpaired electron, therefore paramagnetic, right? And if we compare the paramagnetism of O2 negative with oxygen, so in oxygen we had 2 unpaired electron, here it is only 1 unpaired electron. So paramagnetism will be more for the O2 molecule, right students, oxygen molecule.